We've all consumed sugar in some shape or form, whether it be a nice cup of coffee or a sweet strawberry jam. You may have noticed that sugar is not always present in its crystalline form. In both of these examples, sugar is dissolved in a solution, making the food taste much better.
You probably aren't wondering right now, how did the sugar end up in solution? Well, we're gonna tell you anyway. In this video, we'll explore the three main factors affecting the rate at which a solute dissolves in water, using sugar as an example. The factors include the amount of agitation, the temperature of solution, and the grain size of the sugar crystals. The first aspect regarding the rate of dissolving involves the agitation of the solution. Have you ever noticed when enjoying a cup of joe or tea, when adding sugar, stirring the drink allows the crystal grains of sugar to disappear quicker? This is a direct result of mixing increasing the rate of dissolving. Why would the mixing of a substance result in the increase in rate of dissolution? The short answer is that the swirling motion moves solvent particles around. But why would the movement of solvent particles matter? Imagine the tea mentioned previously. Without stirring, the sugar particles are in contact with the same tea particles constantly. Consequently, the dissolved sugar will encompass the solid sugar particles, slowing down dissolution. On the other hand, if the tea were to be stirred, fresh tea particles would come in contact with the sugar particles, while moving the dissolved sugar particles away from the undissolved solute. Understand that while the rate of dissolving is affected by agitation, solubility does not differ.
The second factor affecting the rate of dissolution is the temperature of the solution. Just like how when we warm up before doing exercise, sugar dissolves faster when the water is heated up. At a higher temperature, water particles have higher kinetic energy, causing them to vibrate faster in solution. These energized water particles collide with solid sugar particles more frequently, causing them to dissolve faster. We use the term rate of dissolving to measure the speed at which a solute dissolves in the water. Keep in mind, sugar is also more soluble in water at a higher temperature. To avoid confusion, we won't go into detail about the changes in solubility, because that's a whole different topic on its own, and it's not the same as rate of dissolving. Without further ado, let's see an example of the faster rate of dissolving. As you can see, with a lower temperature, the sugar takes much longer to dissolve. In the clip on the left, the water is heated to a boil, causing the sugar to dissolve rapidly. Meanwhile, on the right, the sugar takes a very long time to dissolve because it's at room temperature.
The third and final method of increasing the rate of dissolving is through having a larger surface area. Essentially, a given mass of solid solute has greater surface area when the individual grains or crystals of the solute are smaller. What this means is essentially that the greater the surface area, the greater the rate of dissolving. Moreover, greater surface area increases the rate of collisions with solvent molecules, which makes the solute dissolve more rapidly. As we can see here, we have the rate of dissolving for a single sugar crystal. The surface area of a sugar crystal is much smaller than the total surface area of its same mass in granulated sugar. Essentially, less of the sugar is in direct contact with the water, preventing most of it from actually starting to dissolve. As a result, the sugar crystal takes a much longer time to fully dissolve. Thanks to Adam's handiwork, we can now see that grinding a solid solute increases the rate at which it will dissolve. Essentially, the granulated sugar, again, has higher surface area, allowing it to make contact with more of the water and dissolve quicker. So now we can evidently see the sugar dissolving much quicker than the sugar crystal.